sistemler bunlar non-linear değil galiba, değil mi?
Well, we will be dealing with linear quantum mechanics. Linear in the sense that the wave function appears as itself. It is not multiplied with itself.
Peki Schrödinger equation'ı non-linear yapan kısım ne? Potential kısmı mı sonra?
No, there is no nonlinearity in the Schrödinger equation. The Schrödinger equation is a linear differential equation. There is the nonlinear Schrödinger equation, but that nonlinear Schrödinger equation basically has this form, minus h bar squared over 2m Laplacian psi. This is equal to, let's say, if this is equal to e psi, this is linear. If we have plus v of x psi, this is still linear. If you add plus lambda psi squared psi, this is Hermitian but nonlinear. So that last term is what causes the nonlinearity.
Hangi fiziksel durumlarda?
For example, do you believe in time travel? Okay, if time travel is possible, the state of your system in the future might influence your state now. So the wave function in the future should be influencing your wave function now. So that is a nonlinear influence.
Solit olmayanlarda da non-linear oluyor hocam. Niye böyle bir şey oluşuyor?
You see, nonlinear differential equations has interesting solutions. One of them is the solitonic solutions. But those are the solutions of the nonlinear equation. So if we want to describe the solitons that we observe in waves, for example, in fluids, you need to have a nonlinear differential equation. Anyway, back to our subject. On the nodes, the wave function is zero. Here. The probability density at those points is zero. The probability density is zero. The particle cannot be found at those points. If we could somehow visualize the probability density of this harmonic oscillator, we will see some pattern that just looks like the interference pattern. Now basically this is an interference pattern because if you just think about the waves are, there's a left moving wave, the right moving wave in the harmonic oscillator, so they will interfere and these are the nodes of that interference pattern. Now this is the energy. If the energy is at that level, the horizontal axis is the x. Well, that dashed line is what I call the psi is equal to zero line. So this line is the psi is equal to zero line. I just put it at the level of the energy, just for visualization purposes. X coordinate is the horizontal coordinate. So that is still the x coordinate. You see, there I am superposing two things. One is v of x as a function of x. The second thing is psi of x as a function of x. So they both have the horizontal axis x. So I just put them on the same graph. But psi is equal to the line. I just may shift it so that it overlaps with the energy. V is equal to E line. Just for, again, I repeat, for visualization purposes. Well, this is for the harmonic oscillator, not the hydrogen atom. That's a three-dimensional problem. Basically, the same principles will be applied there, but we will study it later on. It will apply for the radial equation because the radial equation for the hydrogen atom will be just like the one-dimensional Schrödinger equation.
Peki oraya çektiğimiz çizgide kuantilemiş o enerji state'lerin arasında forwarded bir enerji state mi oluyor?
No. Well, you see, this is, let's look at over here. This is one energy level. E is equal to h bar omega over 2. This is another energy level, E is equal to 3 over 2 h bar omega. The harmonic oscillator, the exact energies cannot have any value in between. But I just keep in mind that the expectation value of the energy can have any value. But the precise energy should have either h bar omega over 2 or 3 h bar omega over 2 or 5 h bar omega over 2, etc. Now, if the energy is h bar omega over 2, the solution will look like this one. If the energy is 3h bar over 2, the solution will look like this one. Now here I superpose three different graphs. One is the wave function as a function of x for the ground state. One is the wave function as a function of x for the first excited state. And the third one is the potential as a function of x. No, I mean, if you just take the superposition of the ground state and the first excited state, most probably it will have some nodes somewhere. Depends on your superposition, of course. If you just take the ground state plus a very slight amount of the first excited state, there won't be any nodes. If you take the first excited state plus a very small amount of the ground state, it will have one node. Are you familiar with plotting graphs in computers? Yes? Okay, you have 1 week to get used to. In the future homeworks, I will ask you to draw some plots. I don't care. I mean, just find some computer code, some language that you are familiar with, MATLAB, Mathematica, COMSOL, or whatever you want. You should be able to draw some graphs, change the parameters, and see how they change. Other questions?
Hocam genel bir soru sorayım mı? Hocam en son kuantum mekaniğinde neden en sonunda bir inverse space'te karar kılmışlar?
It worked.
Onun dışında alternatif bir şeyler denenmiş mi hocam? Yoksa?
Well, there are alternative interpretations. I mean, people did try to insist on the classical picture for quite a long time, using the position and the momentum functions. Well, I think there is the Born interpretation which kind of tries to achieve that. But at least for the time being, the one that survives the tests of time, let's say, is the Hilbert space description. You say it naturally, for example, it incorporates the uncertainty principle. We didn't impose the uncertainty principle. The uncertainty principle just came out of our description in terms of the Hilbert space. Of course, people didn't like it. They prefer to have functions x and p that in principle could be determined by not us maybe, but by some future more advanced civilization. But they seem to have failed.
Non-commutative olması da inverse space'lerden geliyor değil mi hocam?
Yes.
O commutative'ın sıfırdan farklı gelmesi.
Exactly. And because you see how we obtained the momentum operator, we looked at the translations. The translations and the position eigenvalues, they do not commute. Basically, translation changes the position eigenvalue. So that means the operator that generates translations shouldn't be commuting with the position operator. And that new operator we call the momentum operator. And if we identify it with the momentum operator, the classical equations of motion, we had seen that they are already contained in the quantum mechanical description in an operator form. So this description at least can also explain why classical physics works. I mean, it's not that classical physics fails, it cannot explain nature. It can explain nature. within a limited range of applicability. What quantum mechanics tells us is that classical physics works. It only tells us that it also adds that it is applicable only to a limited range of problems, not for every problem. And within that range, it works. Now, what is the wave function? Well, we had already discussed before that psi of r of t squared, absolute squared, this was the probability density. Or if you just take this and multiply it with a very small volume element, this is the probability that the particle will be at the point R around the point R in a volume d cubed R. Well, let's see. We know that this psi of R satisfies this equation I h bar del psi by del t is equal to h psi, which is minus h bar squared over 2m del squared psi plus v of r psi. This is the equation it satisfies. Well, we can take the complex conjugate of this equation. If you want, it will be minus I h bar del psi star by del t. This is minus h bar squared over 2m Laplacian of psi star plus v star of r psi star. Now, I will assume, we always said that the Hamiltonian should be Hermitian. Well, this basically tells that v star should be equal to v. I will make that assumption. Now, I will multiply the first term by psi star from psi star. And the second term by psi. And then subtract. Well, if I subtract, I get I h bar psi star del psi by del t plus psi del psi star by del t. This is equal to minus h bar squared over 2m psi star Laplacian of psi minus psi Laplacian of psi star. Well, since if v is real, let's say, if v is real, then the second terms on the right-hand side, they just cancel each other. Well, the left-hand side is nothing but the total derivative of psi star psi. If you look at the right-hand side, I can write it as minus h bar squared over 2m, the divergence of psi star times the gradient of psi minus psi times the gradient of psi star. Well, this psi star psi, I will just call it the charge density. Now, that's probability density, so we already called it the probability density. I will just give it the name rho. So this equation tells me that del rho by del t is equal to, well, h bar is one of them I can cancel. This is equal to I over 2m divergence of psi star gradient of psi minus psi gradient of psi star. Another h bar. Or del rho by del t plus the divergence of j is equal to 0, where I define this j to be equal to minus I h bar over 2m psi star gradient psi minus psi gradient of psi star. h bar over 2m imaginary part of psi star gradient of psi. Well, that is nothing but what we call the continuity equation. It tells us that the probability is conserved. The integral of rho over all time, the integral of rho over all space will be constant in time. Over all space, this is equal to minus the divergence of J over all space. But the divergence of a vector field integrated over a volume, I can write it as that vector space integrated over the surface enclosing my volume. And at infinity, my wave function just goes to 0. So J is 0 at infinity, so this is 0. So rho dr is just constant, the integral of rho dr. And that is, in fact, why we can always choose it to be 1. Well, this is kind of an interesting equation. You see, Schrödinger equation didn't come with its probability interpretation. So that's our interpretation that we arrived eventually. If you look at this equation, I mean, you are probably familiar with this equation in electrodynamics. Or if you have ever studied fluid dynamics, this equation also appears over there. This is just the flow of things. So if you just look at finite volume, if the density of whatever you are looking at is changing in that volume as a function of time, this equation tells me that that change is due to the flow through the surface. That is, there's a current density. J just becomes the current density. So at first it was kind of, the first interpretation was that this rho was actually the matter density, not the probability density. So the idea, one of the ideas was that, for example, take the electron. Electron is actually spread over all space, and then you just make measurements. And that J was interpreted as actually the flow of electron in the nearby vicinity. So that was one early interpretation of this equation, of the Schrödinger equation, of the rho and of the J. Now let's look at some other properties of these wave function. So I say psi squared, absolute squared, we called it rho. Now, first of all, we can always write psi, if this is valid, as square root of rho times e to power I over h bar, some function of r and t. Rho is by definition a real function. S is also a real function. Now, we will see what S is in a moment in the classical limit. Now, let's calculate what J is in this limit. Remember, J is equal to, if you just look at the definition, minus I h bar over 2m psi star gradient psi minus psi gradient of psi star. This is equal to minus I h bar over 2m. Well, psi star is rho e to the power minus I over h bar s. Gradient of psi is the gradient of square root of rho times e to the power I over h bar s, and plus I over h bar gradient of s multiplied with square root of rho e to the power I over h bar s minus the complex conjugate. Well, let's see, these exponentials are cancelled. So we end up having minus I h bar over 2m rho gradient of rho plus I over h bar, sorry, this is also square root of rho, plus I over h bar rho gradient of s minus the complex conjugate is rho gradient of square root of rho plus I over h bar rho gradient of s. I just took the gradient, just put in the wave function. So the current density is just h bar over 2m minus I rho twice I over h bar rho times the gradient of s. Sorry, this. Let me cancel the h bars. 2's cancel, minus i's cancel. This is rho times the gradient of s over m. Well, if you remember, for example, the charge conservation, the continuity equation for the charge, the current density is just the charge density times the velocity, where this v is the gradient of s over m. So the phase we always say that, okay, the phase, overall phase is not measurable, etc. We take the absolute values, etc. But still the phase, relative phases, they contain some information. In this case, this phase S contains the information of how the probability density flows in space. So that information is contained in this phase. Now let's look at what the equation that this rho and S satisfies. We have our wave function solution over here. What is the corresponding Schrödinger equation? What does the Schrödinger equation become when we put this solution in our Schrödinger equation? Well, let's see. First, let's take the time derivative. This is equal to the time, del by del t of square root of rho times e to power I over h bar s plus square root of rho times I over h bar del s by del t e to power I over h bar s. All of this multiplied with I h bar. Well, just for simplicity, I will only take the terms that don't contain h bar, if you don't mind. So this is equal to minus square root of rho del s by del t e to power I over h bar s plus terms that are proportional to h bar. Now the Laplacian will be kind of complicated. Laplace, we had already calculated the gradient of psi. Now the gradient of psi is the gradient of rho, square root of rho, e to power I over h bar s, plus I over h bar gradient of s, times square root of rho, e to power I over h bar s. Let me take the divergence of this thing. This is the Laplacian of the square root of rho, e to power I over h bar s, plus 2I over h bar gradient of s times gradient of square root of rho e to power I over h bar s, plus I over h bar Laplacian of s square root of rho e to power I over h bar s. this, let me just take the h bar squared over 2m minus h bar squared over 2m gradient of psi. Well, if I only take the terms that do not contain h bar, in the Laplacian of psi, I should take the terms that contain a 1 over h bar squared. Because if you, for example, look at this term, the first term in the Laplacian of psi, that doesn't contain any factors of h bar except in the exponent. If you multiply it by h bar squared, that's a term proportional to h bar squared. Those terms I'm just ignoring for the time being. And the only term that is in the Laplacian of psi that has this 1 over h bar squared is the second term. And in fact, in the second term, if I take in that gradient, take the gradient of the exponent, that brings another factor of 1 over h bar. So this will be minus h bar squared over 2m, 2I over h bar, gradient of s multiplied with I over h bar gradient of s times psi, plus terms that are proportional to h bar. This is the only term that doesn't have an h bar in it. So let's just make these cancellations. H bar squareds cancel, 2's cancel, this minus I, and this minus sign cancels. So this is equal to gradient of s squared over m multiplied by psi plus terms of the order of h bar. I'm missing a factor too. Now let's just combine them all. I h bar del psi by del t. I had already derived this relation. This is minus del s by del t. Psi plus terms of the order of h bar. I know that my Schrodinger equation tells me that I h bar del psi by del t should be equal to minus h bar squared over 2m Laplacian of psi plus v of x psi. This tells me that minus ds by del t psi should be equal to gradient of s squared over m psi plus v of x psi plus terms of the order of h bar. Let's take the limit h bar goes to 0 now. Gradient of s squared over m plus del s by del t plus v of r, this should be equal to 0. I'm missing that 2. There should be a 2 over there. With that 2, I still insist that 2 should be there. I don't see it where I'm missing it. This is called the Hamilton-Jacobi equation. In classical physics, and S is nothing but the action in classical physics. So I'm assuming you are familiar with the action, the Lagrangian. Yes, no, yes. No, you, okay. I mean, if this doesn't make, this is also one of those topics that if it doesn't make sense to you at the moment, just keep in mind that there was such a thing in, that you had seen also in quantum physics, that, well, you basically see that if you solve the classical equation, you get an approximation to the quantum mechanical wave function. S is something that you can calculate in classical physics. And it's also interesting that the gradient of S is nothing but P in classical physics. You see, up to these IH bars, using the derivative operator as momentum is basically there.
Hocam o şeyden sonra bir son 5-10 dakikayı kısaca gözetebilir misiniz? Hangi
Yeah.
işlemleri niye yaptık?
So what I'm looking at is I'm trying to interpret kind of the wave function. What is the wave function? Okay, on one hand we say that it is the absolute value is the probability, but if you take the absolute value, you are kind of missing some information. If it was only the absolute value that is relevant for us, then why are we working with complex numbers? Why not make a formulation that depends only on the magnitudes? And so we are kind of trying to see what the phase of the wave function means. Now, on one hand, we just looked at these current. This is the probability current. It's not actually the matter current as people hope to interpret it at first, but it's a kind of a probability current. As the system evolves, the probability densities at every point are changing, but they are kind of flowing from point to point. And this phase is actually the velocity of this flow of the probability density. That is what that phase is. And then we looked at, okay, do we have any other interpretation of this phase? Kind of one interpretation is over here. It's finished. Now, is it possible to have an alternative interpretation of the phase? So we were looking at the properties of this phase, this function, S. And then what we did is basically, we just put the phase in our wave function, in our Schrödinger equation. We obtained an equation. You see, this 2 is the 2 that's causing me problems now. We put it in the Schrödinger equation. We calculated the Laplacian of psi, etc. No, sorry. Here I don't have the 2. Now I know my mistake. You see, if you take the gradient of this first term, is this term, plus gradient of square root of rho times the gradient of e to power I over h bar s. So you just have this additional term. And then I have the gradient of these ones without that factor 2. So there's no factor 2 over here, there's the 2 over here. So there's the 2 over here. And now I happily have my factor 2. Okay. So, okay, we did all these derivations, etc., just for the sake of putting this expression of the wave function into my Schrödinger equation. And after I put my wave function into the Schrödinger equation, this is the equation I obtained when I took the limit h bar is equal to 0. Now, once you take your analytical physics courses, it will make more sense to you. This is an equation that we have in classical physics. And S is called the action. S is given by the integral of the Lagrangian over time, over a given trajectory. So it's kind of, okay, one problem that the quantum physics had to address is how does the classical physics emerge from quantum mechanical description? So this is also one of the analogies between classical physics and quantum physics. If you know the solution of the classical physics, this S classically, you have an approximate wave function of your system. There will be, of course, corrections, but kind of that classical solution is already in the quantum mechanical, or the quantum mechanical description already contains the classical description. And this S has this interesting property that its gradient is actually the momentum. Now let's look at the gradient acting on our wave function. And let's multiply this by I minus I h bar. This is equal to minus I h bar, the gradient of the square root of rho, h power I over h bar s, minus I h bar square root of rho times I over h bar gradient of s, h power I over h bar s. This is equal to, well, just gradient of s times psi, this is my psi, plus terms of the order of h bar. But classically speaking, this is just p. So p times psi is actually equal to minus I h bar gradient of psi. This is again semi-classically. The identification of the momentum operator as the derivative operator is also itself in classical physics. Up to corrections of the order of h bar. So this is kind of a connection between the classical physics and the quantum physics. Most of the things that we have in quantum physics, most of the formulation is actually embedded in, we already have them in classical physics. Although it seems that we are kind of interpreting new things, they already exist in classical physics. Of course, the interpretation just brings us all new concepts, etc., but the formalism is, in a way, is already in classical physics. Which one? Here. This line. The last line. Of the order. No, that's not Q. These are, it's just a symbol meaning of the order of h bar. Those are terms that are proportional to either h bar or h bar squared or h bar cubed as an overall factor. Well, you see, look at this term. Is it proportional to h bar? So it's of the order of h bar. Instead of writing all those terms, I just use that symbol. That's an O, not a Q. This is h bar is of the order of h bar. Now, especially when you are studying classical analytical mechanics, so now you know what all these formalism of action, etc., they will also serve in quantum physics. Now, in a couple of weeks, we will be studying, for example, the WKB approximation. Well, that's a semi-classical approximation to quantum physics. Okay, yes?
En yukarıda en başta ekoloji yaptıktan sonra kompleks konjügelerini alıp tekrar bakalım dediniz ya.
Hı hı.
Oradaki o motivasyonu ben anlamıyorum. Ne kompleks konjügeleri?
Well, why I wrote the complex conjugate? Because I want to derive this equation, and once I take the complex conjugate, I know that I will be able to reach at this equation.
Evet. Yani sonucu bilip ona göre...
Yes, I know the answer. So that's why I took the complex conjugate. Or if you want, I mean, maybe it could have been better to go the other way around. You see, we have the psi star psi, take its time derivative. This is partial derivative. Del by del t of psi star times psi plus psi star partial derivative of psi by del t. Then from here I can write that the partial derivative of psi star, I would like to express it in terms of terms that do not contain the partial derivatives. That will be just 1 over I h bar, Hamiltonian acting on psi star, psi plus psi star, this conjugate plus psi star 1 over I h bar h psi. And then just use what h psi, I know what h psi is from Schrodinger. What h, if I just use the p squared over 2m plus v of x, I get the previous result. Now, in this derivation, then you can ask, why do we take the time derivative of psi star psi? But it's kind of, I'm basically studying the properties of my wave function and trying to interpret those properties. One of those properties turns out to be this equation. So it is actually a flow of something. So it satisfies this flow. Any questions? Okay, now you can go smoking.